Thank you all for being there today. I'm gonna present the output of my work with Romain Fleury and Mathieu Maléjac at TPFL this summer. And so we'll discuss all those fancy keywords in the presentation, topology of singularities in pressure wave fields. So first, we'll discuss a few review of what is a vortex, what is a saddle point, topology behind those notions, then generalize those notions in 3 dimensions, discuss again about topology, and finally present some new results that we found at TPFL this summer. So in order to make us all speak the same language, let's define what is the Poynting vector in this presentation. So we have the Poynting vector phi that is defined as the product of the absolute value of p squared times the gradient of the phase. So we have the pressure here, see this term, and then we will discuss those 2 colors that you can see there when they annihilate, when they go to 0 in all the presentation. Just in order to make you understand how to represent the Poynting vector, we can use 2 different representations. The one with vectors, so we can emphasize this on the amplitude, but not the direction, because we don't see anything where we don't have a huge amplitude. Whereas here we will use in this presentation the streamline representation, so we won't see the magnitude like this, but we'll see the direction. And to represent the magnitude on those type of representation with streamlines of the Poynting vector, we can just use colors, because then we will be able to see magnitude and the direction of the Poynting vector. So first, a vortex. We have here this p square, and if this p square goes to 0, then the phase is not defined, because you know the pressure is an absolute value times the phase. So we have a singularity of the pressure, a singularity of the Poynting vector since pi goes to 0, and then the singularity of the phase. If you plot streamlines of those singularities, so here you have p equals 0 at this point, and then around you will see some streamlines doing some circles. Same for saddle points. Here it's the gradient of the phase that goes to 0, so it is a stationary point of the pressure phase, and you have a singularity of the Poynting vector and a singularity of the gradient of the pressure phase. If here you plot the saddle point here, you can see that the streamlines will go around, and this is just definition of saddle point. You might know that already. What will be interesting with those points is their topological indices. So we will define 2 types of topological indices. What we call here in this presentation topological charge, and what we call topological index. First, the topological charge is defined in this equation. Basically, what you need to know is for saddle point S, the charge equals to 0. And for any other left-handed first order, or it will go to 1, and for a right-handed vortex, it will go to -1. So what it does is you have a guy that is here that is trying to follow the curve C. So the curve C here is the red curve, and by following it, you will count how many times you round, and then here. For this example, here we would do two rounds, so S would be equal to 2. And then we will define the topological index. So again, the equation looks like, but it's not the same, since here you have saddle points that goes to -1, and any other type of critical points. And here in this presentation, we just see saddles and vortices. T equals 1. So what it does is you follow the curve C and you see the streamlines, and you will try to follow how does the quiver does. And here it does 1 round from 0 to pi. So we have here 1, and for a saddle point, you will do if you follow the C in the left-handed direction, you will see that those quivers goes to -1. So it's just a definition. What is interesting with this is the principle that we can admit, and that are demonstrated in the literature, The first one is what we call the twin principle, which states basically that the topological charge must be conserved in a free space when singularities are either created or destroyed. So generally, it is what is written here. It leads to the creation of vortices of opposite charge with equal magnitude. So if you have a vortex in the right direction, you will have a vortex in the other direction. This is all in 2 dimensions. Then we have the sign principle, again, meaning the conservation of the charge. And it is a bit trickier since it states that the charge must be conserved in any adjacent vortices of the zeros of the real part or imaginary part of the pressure. Let me explain. Here you have in purple the imaginary part of the pressure, that is a line, and you will have the same for the real part. And when those lines intersect, the zeros of the imaginary part and real part of the Poynting vector of the pressure, you will find those vortex points, and the charge will be either +1, then -1, then +1, and so on. So this rule is very important because it allows the determination of the charge of all vortices in a given field. So if you know one vortex, you know its charge, then you will know all the other vortices in your field. Concerning the index theorem, it is the conservation of the index, topological index. Then it's quite easy. It just means that if you have an index, then it will be conserved in some bounded region. So if for example, if you have a vortex, then you will need a saddle point. And if you don't see this saddle point that is lacking, if you just have one vortex, it just means artificially that this saddle point is expelled to infinity and you don't see it in the bounded region that you observe. So it's a bit artificial, but it will be useful. And from what I said before, all those conservation of charge and indices, then we can define an elementary reaction. Basically, you have A, that are vortices, and B, saddles, and you will have this elementary reaction that makes our system stable, that is having a vortex with a charge 1, then a vortex with charge -1, and then 2 saddle points. And then this system is stable. You can just have those that are not trying to destroy them each other. Now we can define what happens in 3 dimensions, which is a bit trickier. What we need to know for now is that phase singularities, so pressure singularities, phase singularities, all are vortices, as we said. They are lines in 3D. So we have not vortex points, but we have vortex lines, which can be curved, but locally we will see them as straight lines. And we will define what is called a dislocation. So this term has been introduced by Barry in 1974 in a very seminal paper that you must read if you like this topic. And we'll discuss in the later what are those 3 types of dislocation. And basically from now, what you need to know or consider is that the dislocation is a synonym for vortex line. But we'll see that it's not exactly the case, even if in literature, some people might use them for each other, and it's sometimes tricky to understand. In the example we will give in the later is using partial wave propagation along the Z direction, but those are very general considerations just for the examples. Sorry. Okay. So the first kind of dislocation we can introduce is a so-called edge dislocation. So the definition is you must have a constant phase along the line singularity. So you have this singularity that is a vortex singularity, and you will define the phase as constant along this line, basically. In the example of the paraxial wave that I gave, you have this line that must be parallel to the x-axis, and we said that the direction of the propagation was along the z-axis. So you will be able to build some dislocation when you have lines that are parallel, line singularities that are perpendicular to the direction of propagation. This is basically what is plotted here. You have those real part and imaginary part of the pressure, and you will see this line that is the intersection, and you can also see it from there when you have the phase from -pi to pi that is constant. So it will be constant if you have the line that threads like this. Okay, this edge dislocation will be very important in the last part of the lecture because it is what we were able to produce with our numerical methods. Another one that is way more common is a screw dislocation. So a screw dislocation, the name is because it forms some helical wavefronts along the dislocation here. So basically you have surfaces of constant phase, for example, phi equals 0, which is simple, with helical form along the line singularity. So it forms some helical form. And how to do it simply with a paraxial wave is having a line dislocation that is parallel to the z-axis, so to the direction of the propagation. So here again, you have a constant phase. This is just the surface of equiphase, and you see it that is doing some helical forms along the singularity. And what we do have in the very general case is a mixed screw edge dislocation, because if dislocation lines are neither parallel nor perpendicular to the singularity, then you have those type of dislocation, sorry, and it is basically a helical wavefront, but it is pitched. So again, you will have some helical wavefronts, and those are definitely the most common because edge dislocation are the very precise case where you have some wavefronts that are parallel, some singularities that are parallel to the direction of the propagation. And those screw dislocation present some interesting features. So here you have a screw dislocation loop, so a closed dislocation line. We can see the phase here in the color here, and it goes from -pi to pi. It is what we can call the topological current. So we can say a topological current of 1, which is a generalization of the topological charge in 3D. So 1 because it goes from -pi to pi, which is rounds when you do a round revolution around this dislocation. And by continuity of the field, sorry, you will see this other dislocation line that is also a screw dislocation of topological current equals to 1. It must thread the dislocation. And this is what is stated here. You have some lines of equiphases, and it must thread in this axle with another dislocation line. Okay, so you might wonder, why am I telling you that? It's just to introduce the further notion. Let's just do a little parenthesis to what we say. It's just defining in 2 dimensions higher order vortices. So here you have a vortex of topological index equals to 1. So this was the case we studied before. And you can have higher order vortices with t equals 2, t equals 3, t equals 5, and so on. So it looks like a bit like multiples or whatever you want to see. But it is very interesting because those vortices appear in 2D, so they also appear. Those vortices appear in 2D, so they must also appear in 3D. And how do they appear? Like this. It is beautiful, but a bit difficult to understand. So what it means, we will take it slowly. Let's imagine that you have a dislocation loop like this here. Okay, first, let's imagine you have a dislocation loop and you have a current, topological current equals to more than 1, like let's say 2. So this is basically what it says here. You have a loop of currents n equals to 2. We'll put this. And you have, it is shredded by another dislocation, and dislocation has a current equals to 3. It is totally unstable, and so we'll have this thing that is the unfolding of the dislocation, and you will see it is a knot. So you have there here only one dislocation, so you can follow the path. It will just be one dislocation, but it will have a knot inside. And if you have okay, it creates knots because M and N are coprime. And if you have M that is not coprime with N, then it creates links. So basically here what you have is two dislocations that are linked together. And then it must again be threaded by other dislocation. All we see here is screw dislocation. Okay, let me finish with the 3D case by speaking of the representation of the 2D case. So basically what we have here is this line is a vortex line, so dislocation line, and you will have the small rotating loops all there that are just a way to represent the topological current. Here we have just like one loop to say that we have a topological current of 1, let's say, in the direction of the dislocation that we define here, N, and you can follow the current along this dislocation line. So what you need to understand is this line is only one vortex, but a 3D vortex line that propagates in your field. And if you see, when we were speaking about 2D vortices, it's just what I plotted here, sigma, it's just a plane that, and this dislocation threads 3 times the plane sigma. And what you see in 2D is the topological charge, and you will see the vortex of charge here 1, here -1, and here 1. So this is the conservation of the charge that the rule that we said before. So what we see in 2 dimensions is not the reality, because in 3D it's just one dislocation, and from one dislocation you will see 3 vortices. So that is why it's a bit tricky. And you can also define the index trajectory that has a discontinuity here, because as all of those points here, here, and here are vortices, then their index are 1. So they are always in the direction of the top, in the front of sigma. So, but the index here is not very important. The idea is to understand that what we see in 2 dimensions is, for example, 3, in this case, vortices, but those define only 1 vortex line in 3D. We will finish about the review of the field with the so-called Berry's paradox, which is a problem that was been described by Berry, of course, and it explains some problems that we can encounter when we try to represent 2D fields, 3D fields, sorry, by foliations of those 3D fields. So basically what is a foliation is just a lot of 2D planes that are in the same, that are all parallel altogether. So here we have a foliation, and what it says is there is no observer-independent stationary point trajectories. Let me explain. A stationary point is basically a saddle point or other type of critical point that we won't discuss today. But what we must understand from this law is that there is no observer-independent saddle point trajectories. Okay, what does it mean? Let's have a 3D field. So this is just analytically plotted things with basic operations. So here you have a 3D field, and you want to describe it by planes, 2D planes in the same foliation. So here you just plot it in the XY plane, and you will be able to see here a vortex and here a saddle point. If you zoom on it, you will see a vortex and again a saddle point. But if you use another foliation, let's say XZ, you will see again the vortex, but you won't be able to see the saddle point. This is what it means. It just means that be careful if you want to describe your 3D field with vortices and straddle points by 2D planes, you will have a lot of information because you will be able to have the vortices, but you won't be able to have observer independent saddle points that are observed. So we can't define easily with this saddle lines. And we will try to bypass the various paradox in the work we did this summer. Okay, let's explain what we did. And the first thing will be to discuss results by Ruben and Paganin in 2007. They were just using spherical point sources and creating singularities of the pressure field or optical field or whatever you want. It's all, if you consider a scalar wave field. You have here 3 point sources, and by the interference of those sources, you will define some dislocation line. So here they use, for example, a phasor way to observe those type of singularities. Let's say you have P1, P2, P3. Those are 3 phasors with the amplitude of the monopole and the phase of this monopole. And if you're able to have a closed loop, a closed triangle here, then you have these singularities because it goes to 0. This is what it states here. And what is important here is they have, so 3 spherical point sources. They put the phase O to 0. And so we have interferences because those sources are not in the same point, obviously. And we have a lot of singularities of vortex lines everywhere. And we'll try to understand what happens to those vortex lines in 3D in what we did. So what we did was trying to define a point where we would have a 0 of pressure. So this is what is done in this equation. You just basically say that P must equal to 0 when you have, let's say, an even number of monopoles with the same time. If, for example, if you have 4 monopoles, let's say you have 2 monopoles, they are all at the same amplitude. You have 2 monopoles with phase 0 and then 2 monopoles of phase pi, and then you'll be able to define 1 point, 1 coordinate, which is the target x, well, xt, yt, zt. And at this point, this equation will annihilate and goes to 0. This is what is stated in this equation, and this is what we do in the laser. By doing this, we find those fancy curves. Okay, let me explain what it means. You have those sources that are represented here. So we use here 2 sources, but we did the same results with 4 sources, 6 sources, and so on. We have 2 sources that are very, very close together, and we have a target point that is here. What we see at first point is a huge vortex line, a vortex loop, so a closed vortex line. That is the kind of ellipse that you see here. And if you want to try to plot the streamlines in 3 dimensions and not in 2 dimensions, because in 2 dimensions you will lose information because you're in the Bayes paradox. So you use 3D streamlines, and you will be able to find those singularities that are represented in color. What happens is you have this singularity line. You zoom on it, you probe it, and then you'll be able to find those points. So this line you see is something that has something about 10 lambdas in dimension, and this is very, very small because those plots, all those small plots, are zoomed 300 times. So if you zoom on the green box here that you have there, what is there is something that has the order 10 and the power minus 2 lambdas. So you have something that is very, very sub lambda, and you have a huge loop that is something about 10 lambda. And you just see this singular line loop, and not all those loops everywhere and lines everywhere that they saw in Pagan-given explanations. And if you zoom on those points, on those singularities, you will see this. And this structure is a saddle vortex structure in 3D. So you have not only one loop here, but we have two loops that threads here, because this loop is a zero of the pointing vector. So if you look at it from far away, you will just be able to find one loop, because you won't see what happens at 10 at the power minus 2 lambda. But if you zoom on it, if you probe it, you will be able to find two loops that threads this structure. And here you have a vortex, and here a saddle point. So here the colors define the magnitude of the pointing vector. So you can see from the blue colors that at both saddles and vortex lines, then the pointing vector pi goes to 0. So this is what is explained for you to be able to understand what I said in those plots. So basically, here are the surfaces of zeros of each direction of the pointing vector. So surfaces, they cross into lines, and you have two lines, a line that defines a saddle point, and a saddle line, sorry, and a line that defines a vortex line. And here, you can have another representation if you want to separate what happens from saddles to vortices. So you can have zero of the gradient of the phase of the pressure, which is a line that is the saddle line. And you can have zero of the intersection of the surfaces of zero of the real part and imaginary part of the pressure, which define the vortex line. And this structure, it can be defined in another way. It can be defined as a loop edge dislocation. That is why I said it was tricky to speak about vortices and dislocation as the same notion. It's only because here what we state is that an edge dislocation must be the sum of a dislocation line, of a vortex line, sorry, and a saddle line. So if you take again the definition of dislocation, of an edge dislocation, you needed to have the phase that was constant along the dislocation. But as we know, at the vortex point, the phase is not defined. So we need to have both the vortex plus the saddle to define this dislocation. And we can see it from this plot, because you have here, so, okay, you might not be able to see it properly, but you have here surfaces of the phase, and we can see that it goes, it just follows the direction of this huge dislocation that is seen from far away. And if you look at what happens to the phase when you just cut the dislocation line, then you see that the phase goes, this is quite unzoomed, this is quite far away from the vortex saddle structure. You will see that the phase goes from 0 to pi or minus pi to pi, as you wish. And basically, this plot is exactly what we find in the literature, because, okay, this is our plot, and this is what it finds, what we can find in the literature. So you have this dislocation line that threads this plot, and you have the phase that goes from minus pi to pi. So what we say is you need to have a vortex plus a saddle line to create a so-called edge dislocation. What we can do is trying to manipulate this huge dislocation line composed of two vortex plus saddle lines. So here you have different dimensions. So here, for example, something that is something like 0.5 as a diameter, and here a bigger one. And what we try to do right now, Mathieu Maléjac is still working on it since this summer, is trying to understand how this loop is formed. And basically, we just had two monopoles. We create this loop, and we can have different things that we can change. We can change the distance between those monopoles. We can change the distance from an axis of symmetry of the system. And what we could define three lengths that let's say three characteristic lengths, of the dislocation, namely the diameter of the dislocation, then the distance between the vortex and the saddle inside the dislocation, and the distance from of the dislocation to the source. So three characteristics, and basically what we're trying to do is try to mix all those parameters to make different sizes of dislocation. But what we still have here is, if you just see the zeros of the pointing vector here, you won't be able to see the vortex and the saddle. You will just see a huge dislocation, but if you probe it, you will see two types of singularities inside of it. So we can just sum up a bit. So what happens? So by plotting in 3D some streamlines, we bypass the various paradox because we are not still in 2D, so we can see saddle lines and vortex lines. And from what you can see here, this is not typically generally an ellipse. It's just a closed dislocation line. So here, for example, you have this small curve, so it just defines that it is not a 2D singularities. It is just something that goes in 3 dimensions. And the work of Mathieu will be to understand how can we manipulate this dislocation and how does it work, and it can be folded, can we create dislocations of dislocation, and so on. And it is very difficult to probe the loops together because some are, so this dislocation line is something like 10 lambda, and this vortex saddle structure is 10 minus 2 lambda. And so the idea would be to do an experiment, but again, it is quite difficult because imagine an anechoic room, you create with 2 monopoles, okay, easy, you create a dislocation, but see, for now, the dislocation is something like 10 meters. So you have 10 meters of dislocation, but the singularity itself, if you want to prove that you have saddles and vortices very close together, then you need to probe something that is 10 minus lambda, minus 2 lambda. So it's very difficult. So that is why at this point, we try to manipulate those dislocation to make them comparable, like the characteristic lengths comparable. See the diameter of a dislocation compared to the distance between vortex and saddle lines. And it will be technically feasible, but we will also need to have something that probes the pointing vector very well. So we will need to have probably something 10 at the power minus 1 or minus 0 lambda if you want to probe correctly the distance between saddles and vortices. And the last thing we'll try to do is perturb the loops. For example, if you have a scatterer like from put here, let's say a small sphere, you put the scatterer on the loop. Can we have something that perturbs at 10 at the minus 2 lambda along 10 lambda, and you will have those 2 dislocations that will be destroyed, those 2 singularities that will be destroyed? Well, I guess. And the only thing is, for now, we need to think a bit more of just putting a scatterer on the pressure singularity, on the vortex singularity, because if P equals 0 at this point, then we won't do anything with putting a scatterer. So we would need to have a bigger scatterer. But the idea would be, it would be quite, not incredible, but quite fun to be able to have a scatterer that perturbs something that is at 10 lambda, but the inner structure is 10 over minus 2 lambda. So that's it. Thank you very much, and let me see if you have any question, and I will be very happy to answer.